Good afternoon. I'm here to give the presentation of our research paper named Visuomotor Influences of Attached Robotic Neck Augmentation. I'm Lichao Shen, the first author. In brief, this research is motivated by the issue that human eyes has a limited field of view. Human eyes have a relatively narrow spatial range of vision comparing with the animals such as a bird or rabbit. The binocular vision, which means both eyes seen at the same time, is about 120 degrees wide and 135 degrees tall. In the attempt to explain the spatial range of vision, the most direct approach is to extend the field of view of human eyes directly. It can be expanded either by getting the image from a camera or a lens with a wider field of view, or by stacking the image from multiple camera areas to combine a wider field of view. Such approach of directly visual augmentation typically requires training and adaptation by the user, and the stereo vision was ignored. So why not try another approach? A new method maintains the visual property of our eyes, including field of view and binocular vision, and to reduce the adaptation time. Let's examine what limited the vision range in the space. The action shifting the visual field in large scale, we roughly call it scanning. Our eyes need motor assistance from the body to expand the spatial range of eyesight. Elbow, neck, and torso are all likely to involve in scanning the environment. Then we find the assistance from the neck are more significant than the rest of the body, and the coordination between the motion of the neck and the vision of the air are more significant. That's because the neck is at a balanced point. The neck directly connects to the hand, and it drives only the hand. Thus, its range of motion is relatively wider than the elbow, and its motion load is less than the torso. Existing research has shown the type of scanning motions that depends on the different final target position with respect to the hand. When the target locates outside a specific range, the neck motion is very likely to happen. Even more, beyond a certain range, only the neck motion will happen. Therefore, we choose the neck to be augmented. Look at the range of neck motion. It has 3 degrees of freedom, and it can operate in 6 directions. With the neck motion, human eyes can cover all the front hemisphere, which is half of the surrounding. It's much better than the situation without the neck motion, but still not enough. So we need a robotic neck to augmentation the neck motion. Introduced to the robotic neck system called unconstrained neck. First, watch a short video to have an overview of this system. So from the video, we can see the device obviously expands the range of hand motion, and therefore extends the range of air vision and the scanning range. The neck vision relationship can be modified and programmed by this system. As the photo shows, the system of unconstrained neck consists of 3 degrees of freedom robotic neck holding a stereo camera. The robotic neck consists of 3 servo motors, and each servo drives the rotation motion about one axis, that is, yaw, pitch, and roll. The internal mechanisms are defined in the controlling software. The vision have two parts, spatial info and imaginary contact. We merely modify the orientation of the vision, while the imaginary contact of the vision remains unmodified. The system input is the original vision, that is what the eye can see in natural conditions, and the system output is modified vision, that is what the eye can see wearing this system. On yaw, we use the hand rotation as the input and the camera orientation as the output. The vision orientation mapping about three axes can be built respectively and can be denoted in function groups. And the mapping about one single rotational axis can be illustrated with graph. The x-axis is the input vision orientation as well as the hand orientation. Y-axis is the output vision orientation as well as the camera orientation. We have two very basic mapping. The first one called original, which means natural condition output is equal to the input, nothing is changed. The second called linear multiplied by 2, which means enlarge the range twice in a linear algorithm. Thus, output is simply equal to twice of the input. Certainly, we can draw more mappings such as nonlinear mappings, asymmetric mappings, reversal mappings, or non-mappings. Anyway, all the following experiments in both study 1 and study 2 are conducted with augmented mapping of linear multiplied by 2. The key of the mapping is to enlarge the range twice. The human eyesight can therefore achieve omnidirectional observation or simply 360-degree vision. As shown in this photo, when the user's hand is at a yaw angle of psi, the resulting camera vision is at a yaw angle equivalent to psi due to the combined movement of the human neck and the robotic neck. The rotational angles of the camera are always twice as large as the rotational angles of the hand. Then we conduct user tests to evaluate the influences. This is a video clip during the user test. It shows how the user follows the procedures. From the screenshot, we can also clearly see the relationship of the mapping between input vision and output vision. This is linear multiplied by 2. The procedure of each loop is just like a shooting game. The target will be generated randomly in the space, and the user are asked to aim and shoot at them. We set up following 5 conditions to conduct the user test: 2 for study 1 and 3 for study 2. And we can see the distribution of target location in the space. We use study 1 to explore the vision-neck relationship. In study 1, the condition 1 uses the original neck mapping. Condition 2 uses the augmented neck mapping. The virtual target is the yellow sphere in space. To aim means to put the sphere within the circle mark in the HMT vision. The procedure of study 1 consists of small loops. A loops have step 1, the user aim at the original point. Step 2, the user press key, find appears, a target is generated. Step 3, the user rotate hand to find and aim at the target. Step 4, the user press key again, current target is destroyed, back appears. Then it will loop from the step 1, resume to the original position. We measure and record the response action of scanning. Target 10 is the 10 cost to complete aiming at a specific target from the initial location. That is the interval between the moment one target appears and the moment the next target appears. Condition time is defined as the total time cost to complete all 4 repetitions and for all 20 targets. The overall result of condition time from study 1 are depicted in this box plot. The box plot shows the average condition time for 14 subjects. Here we can find that the users are able to aim at the virtual target faster in condition 2, that is with augmented neck mapping, than in condition 1. Results are further analyzed using a t-test. We got a p-value showing significant differences between two conditions. That is, the time decreased and the speed increased. The result of each target time are depicted in this line graph. We find those significant difference mainly happened in the range from longitude 150 to 180. In order to remove the influence of target location displacement to the target time, we use the target speed to examine the result. Then we find the target speed have a peak, usually appears around longitude 120 and or 150. And after augmentation, the peak will become higher and move right. Simulator thickness questionnaire and neck load questionnaire are carried out to evaluate the system performance. The t-test shows that the VR thickness did not increase, but the neck load decreased. So we can have some conclusions from study 1. Firstly, unconstituted neck have positive influences. It enlarges the spatial range of vision and augmented the response motion. The range becomes 200% as wide as before. The response speed becomes 128 as fast as before. The response time becomes 78% as long as before. The effect is uneven and will be influenced by target location and user. We use study 2 to explore the hand-involved task to see what would happen when doing task with hand. The condition 3 using the mapping of original neck and original virtual hand. Condition 4 using augmented neck and original virtual hand. Condition 5 uses augmented neck and augmented virtual hand. The virtual hand mapping was defined in similar way: physical hand position as input and virtual hand position as output. The procedure of study 2 is almost the same as study 1. The only difference is before press key to destroy the target, the user needs to operate the virtual hand to reach the virtual target. Virtual hand is a white sphere controlled by the remote controller. To reach means to overlap the virtual hand with the virtual target, and the virtual hand will turn green. The overall result of condition time from study 2 are depicted in this box plot. Post hoc test reveals the comparison between 3 groups, and there are differences between condition 3 and condition 5, and also differences between condition 4 and condition 5, but no difference between condition 3 and condition 5. In study 2, significant differences mainly concentrated in the range from longitude 120 to 180. Study 2 next task load index shows the augmentation of neck and hand in the same time do have positive influences and reduce task load. For the hand-involved task, however, a normal virtual hand with a normal virtual hand, the overall influence of the unconstituted neck was weakened to an insignificant level. And with the augmented virtual hand, the overall positive influence was recorded. Possible explanations are those. First, the hand always have a higher property to the neck in the spatial perception, especially in this hand-involved task. Second, the disorder caused by a conflict between two spatial reference objects reduced the influence. As future applications, the technique of alternating surmount coordination and its further implementation could have a beneficial application in research, entertainment, sport, and other scenarios. In addition, we are considering similar techniques to be used to explore more novel visuomotor relationships. For instance, this is another work in progress. The main mechanism is using both hand and head to control the vision orientation, something like a transparent else to hand palm. This is the end of the presentation. Thank you for your listening.